Hello. I think we can start now. If you have any question, you can ask. Today we will um, have the office hour.
How is the exam going to work? Is it gonna be proctored online, or is it gonna be more like a take-home exam?
I will post the examination as a PDF on Canvas. You can download it from Canvas. I have no requirement on the on how you perform your examination. You can Google it. You can read our slides. You can do anything um, when you perform the examination. My only requirement is the time. You have to submit your answer on time. We have 1 hour and 15 minutes. Um, so I presented maybe 10 problems in lecture 10, the last lecture we have. I may select 7 or 8 problems from that 10 questions. I cannot guarantee we will have 100% the same problems as those problem from the last review slides, um, but they should be similar. I will only change the numbers in those questions. Um, and still, we have two new questions, which you never seen in the which you never seen in the review slides. But I believe if you fully understand the problem in the slides, you should be able to do that two new problems. In this way, I think most students can have a very decent score for the examination midterm. And for the best students, of course, he or she can maybe get a full score, 100. So we will have 10 questions in the examination. Each question may cost 10 points. Yes, I received some questions. I will try to answer them. We have 1 hour and 15 minutes for the examination. I will do the floating point conversion. So I think the floating point conversion is a important question because nowadays, due to the machine learning, people pay more attention on this floating point standard. Um, they create a less per session floating point format with less per session. For example, 16-bit floating point data type and even 8-bit floating point data type. So the encoding of the floating point per session can be seen from here. This is the sign bit. This is the exp. Exp indicated exponent, but it's not exactly the exponent. It's an exponent with a bias. And then we have a fraction. So we have 3 parts. You can find the definition of these 3 parts here. The most significant bit is the signed bit. We have the exp field. We have the fraction field. And of course, we have different sizes for one floating point number. We have a single per session, which is 32 bits, double per session, which is 64 bits. Besides these per sessions, we also have other per sessions, which is actually defined by different companies. So they may not be a IEEE standard. They may only supported by some particular company like the Intel or AMD. They have their own version of floating point format, but it's not fully compatible with other companies. So these two, the single and the double per sessions, are the most important one. So you can see, because the total bit budget, which is 32 and 64 bits here, we have a different bit for different parts of the floating point per session. The signed bit is always cost you 1 bit, only 1 bit. But for the exp and the fraction, you have a different bits here. So let's take the single bit per session as one example. The single bit has an 8-bit exp, 23 bits as the fraction. So we only consider the normal case, so-called normalized numeric numbers. By normal, I mean the exp cannot be all zeros or all ones. You can check the previous slides. We have the definition for the exp when the exp is all zeros, all ones. But in this normal case, we don't consider these special cases. So the exp, the exponent, is actually encoded as a with a bias, I as a biased value. So the exp is the number we will encode in this floating point format. This is the exponent itself, and this is a bias. So the final number we will encode it into the binary bits is actually the exp. The exp is equals to e plus a bias. The biased value, different precession may have different biased value. For example, the single precession has a bias value as 127. Double precession has a 1023. So you can, in general, you can calculate the bias like this. E is the bit number of exponent bits. So in the single precession, you have 8 exp bits. I'm sorry. So when you plug that 8 bits here, for example, 228 minus 1, you have a 227 B. You have a 227 as the bias. 227 is exactly the 127. I'm sorry, minus 1. Here you also need to minus 1. This number is exactly this 127. 27. And for the fraction, you just normalize the number into the 1 point XX OX format. The X OX here indicates the fraction, the bits of the fraction. So the minimum value is all zeros, maximum value is all ones. Because we always normalize it to 1 point X format, the leading one is free. You don't need to record this one into the, this fraction bits. You don't have to record that leading one. We just give it a 1 by default. So even for the minimum value, if you have all zeros, you still have that leading one. This is 1 point all zeros. 1 point all zeros. It's not all zeros. A real all zeros is a 1 point all zeros. So compared to the E part, the fraction part should be easier. All you need to do is do a normalization. Normalize this number to 1 point something, x. The x is the fraction part. You just get rid of the leading one. We don't need to encode the leading one into the final binary bits. So here is one example. If I put a IEEE floating point conversion problem into the midterm, I will give you the floating point number here. And I will also give you the binary bits of this floating number. For example, these are the binary bits. This is the base 10 number. This is the base 2 number, binary bits. Again, when you get the bits, the first thing you need to do is to normalize it to 1 point something format. This is that format. Because there are 16 bits here, you need to use a 2, multiply 2 to 13. This is 13 bits here. These are 13 bits, I'm sorry. That's the reason why we need to multiply 2 to 13 here. So the m, the fraction here is 1 point something here. Because we will eliminate the first leading one. This is the default one. We don't need to record it into the final binary bits of the floating point number. So we delete it. And then we have 12 numbers here. We have exactly the 12 number here. You can see these two numbers are the same. They are the same, except we delete this leading one. We have 12 bits here. And then we can see that we have, for the single precession floating point, we have 23 fraction bits here. Okay, so but here we only have 12, so we need to change it, convert these 12 bits into 23 bits. What we can do is to insert zeros. We insert, I think 11 zeros here, so that 12 plus 11 is 23. So so we get the fraction here. We have the fraction here. The e here, exponent here is 13. And we know that we have a single precession bias is 127. This is 127. So the EXP is actually equals to 13 plus 127. So the result here is 140. We need to convert this result to binary format. This is the binary format. Since we only have 8 bits for the EXP, so these are the 8 bits, which represent this 140. So if you only have a very small value, these bits should be zeros. The most significant bit, if you have a very small number, most significant bit should be 0. But you have 100 something, so here is a 1. But totally you have 8 bits here by the definition of IEEE floating point single precession format. Then we can put them into the binary format. So the first bit is the signed bit. This is the signed bit. Because it's a positive number, so this is a 0. And then we put the EXP into the binary bits. These 8 bits is EXP, which this part. So this is the fraction. This is the fraction. Fraction we have from because the first bit is the default leading one, so we delete it. From this bit to here, we have 23 bits. These 23 bits represent this fraction. Because this is only 12 bits, we can insert zeros. That's the reason why these are zeros here. Any question about this? So if no question, we will pass this IEEE conversion. Then I will go to the problem. Okay. So I will select 8 problems from the review, and 2 new problem. No. I don't think we have that 2 new problem in the slides. So the 2 new problem may be some combination of those problems in the slides. So they are new. You shouldn't see those problems before. But if you fully understand the problem in those slides, I believe you have no problem with that. You should be able to do that. The point here is that for most students, if they carefully review the problems in the review slides, they should be able to get a very decent credit. For the best students, of course, if they fully understand those problems, they can get maybe 100 points. So any other question? I will just stay online. If you have until maybe 10:30, I will stay online until 10:30. If you have any question, you can ask. Otherwise, I will just mute myself and wait. And also, we don't have any special requirement on the examination. You can during the examination, you can Google, you can open the slides I posted on Canvas. You basically can do anything. But please, submit your answer to the Canvas on time. We are only sensitive to the timing, and also do not call your friends in the same classroom. Having the same examination. I cannot prevent that, those cases. Okay. If you have no question, I will continue to wait.